TRI Beja. I have made it. State. This is university. I went there. She had come to conference in Vancouver. In Hyderabad. No, I did not attend, but I attended the conference and just applied for that. Asian in South Korea. I see I am in China. No, not of mathematics, let's apply. Like yeah. Companies. Still I am. I see I am. July 17 to 21st. From here to there without the paperwork and stuff. Because she has funded me full amount. Okay. हो गया टाइम नहीं है.
Is it 2:30?
So sir.
Oh, 3:30. Right, sir. We can start, right? So again, let's recall the definition of a value function. Vt of x is we are choosing the control u and taking the infimum over all now controls are control processes and the state starting at time t from the state x, the cost to go. Now one thing I would like to put here, strong solutions or weak solutions, we are taking expectations, so it doesn't really matter, because once you take the expectation, it's only the law of the process that matters and not the sample paths. The other thing I wanted to specifically mention is that sample path of a stochastic process is a mathematical object. It cannot be observed unless you yourself is generating the noise. Suppose this is Wt, and that will come very soon in dynamic programming, perspective behind dynamic programming. This noise is an underlying noise. Because we can't model things or we can't do many things, we add a noise here as a part of modeling. Now this noise is not an observable quantity. What is observable is xt or some other function of xt, but certainly not the noise. And since the noise is coming due to various uncertainty, we are not generating the noise. For example, if you are observing stock processes, stock market, you are not generating the noise yourself. Noise is getting generated by the market and various other uncertainties. So this noise is not really observable. So we are not generating the noise and therefore we cannot observe it. We don't observe the noise. And if we are not generating the noise, the sample paths of xt is only a mathematical object, you cannot observe it. For example, suppose there is a stock market, there is a stock st. Now you have made an observation at time t1, you have made an observation at time t2, and so on, t3 and so on. These are the, you know the value of the stock at time t1, at t2, t3, tn and so on. Now at this point, somebody is generating the noise, it has come from some sample point omega 1. Now when you are making another observation T2, nothing is guaranteed that this omega 1 is again here. It may be some omega 2. It may be some omega 3. It will be omega n, and all these may be different. So what you are observing is xt1 omega 1, xt2 omega 2, xt3 omega 3, and so on. These are not sample paths. So if you are not generating the stochastic process yourself, you cannot observe it. So sample paths are mathematical objects. Now too much emphasis is given on sample paths by, of course, the statisticians and physicists. Okay, they draw pictures and estimate various things, so they have to talk about sample paths. But in mathematics, sample paths are very nice mathematical objects. The sample paths of Brownian motion and diffusions are very interesting. Their properties are very interesting. Insofar application is concerned, it's only the distribution of a stochastic process that's important. In any case, stochastic process is a probability distribution. So it's strong or weak, it doesn't matter, we are taking expectation. Now I will write down the stochastic dynamic programming principle. Dynamic programming principle will read like this: Vt of x will be equal to infimum over all, of course, EUTX T2 some tau where it's tau. Tau is a stopping time. It may be deterministic. It may be. In many cases of practical interest, you have to break up not only at a deterministic time, you may have to break up at a random time. And whenever we talk about a random time, we have to talk about a filtration with respect to which it's a stopping time. So in this case, what is the filtration? The common thing is the filtration will be, Ft will be the filtration generated by the process, because that is the observable quantity. Xt is the observable quantity. So realistic filtration is Ft generated by the state process, and therefore tau is a stopping time with respect to that. Now Shaiju has given a proof of dynamic programming principle for deterministic control, right? You have given it, right? By patching up two controls. Now you try to patch up controls in this. So what you have to do is, you have to take u of t as u1 of t, t less than or equal to tau, less than or equal to, doesn't matter, u of t, this. So you are patching up not two controls, not two measurable functions, you are patching up two stochastic processes, and they are not arbitrary stochastic processes, they are stochastic processes. This stochastic process u1t is based on, adapted to the information available, right? So you are patching up, whenever you patch two controls, that is where things go wrong. So the proof of stochastic dynamic programming principle is far more involved than the proof of a deterministic. You try to mimic the deterministic case and you will get stuck. It doesn't work. The reason is, if you patch up this, automatically u becomes a feedback control, because tau is a stopping time which you are using the information of the past of this stochastic process. So even though u1 and u2 are two stochastic processes which are non-anticipative, given stochastic processes, you are switching. The moment you switch, that switching will involve the information of the past. And the moment you are using any information of the past, your control is going to be a feedback control. And therefore, if you want to prove dynamic programming principle, you have to worry about, if it is a feedback control, what is the information that we have. Now, one easy way out, and this is done in many books, this is how this is done. So, what is my filtration? My filtration is, this is done in innumerable number of books. Not finding this filtration will be an exception, finding it will be a rule. Now, this is the filtration. Normally what people do it everywhere, including finance, is that the filtration is generated by the noise. If the filtration is generated by the noise, then there is absolutely no problem. You take a non-anticipative functional U1, so what is your control there? If this is the case, then what is U1 of t? U1 of t is a non-anticipative functional of the Brownian motion. Ut of t is another non-anticipative functional of the Brownian motion, and you are switching at a time which uses the information of only of the Brownian motion, right? And therefore, this is another non-anticipative functional of the Brownian motion. And under a non-anticipative functional of the Brownian motion, since the Brownian motion is given to you, this has a unique solution. There is absolutely no problem. This will admit a unique solution under reasonable conditions. There is absolutely no problem. So, this is one way of circumventing the dynamic programming principle. The question is how realistic this is. In my opinion, this is not at all realistic, because Brownian motion is never observed. Brownian motion is the underlying noise. This is not an observed quantity. What is observed is xt. And therefore, I cannot say that I will use a control based on the Brownian motion. And therefore, there are many proofs of stochastic dynamic programming based on this. And they are mathematically correct. From a practical point of view, they are not really acceptable. Then what do you do? If I discard this and go back to what I think is the right filtration is this. Then if you switch at a random time or even at a deterministic time based on information of the past, this becomes a feedback control. And under a feedback control, general feedback control, this may not have any solutions at all. And in many applications, particularly in finance application, you will find UT here. You will find UT here. In all finance applications, you will find control entering the diffusion also. And you will not be able to find any solutions if UT is feedback. Then there is a way out, and to do into the way out, one would need the concept of relaxed control. So, I am stating a theorem, and I will just give a hint of a proof, not a proof. So, since I will not write the detail, I will quote it. So, here is the equation dxt equal to btxt ut ut plus sigma xt, no control, where ut is a relaxed control. So, if you want to change to my earlier notation, let us write it as ut. It is a relaxed control, and therefore, there is an integral here. So, here is the theorem. If xt mu t, let us call this as star, satisfies star with a given omega f p x0 w. That means the probability space, the initial random variable and the Brownian motion is given to me and I have a solution. For example, for a non-anticipative control, under reasonable assumption, this has almost surely unique solution. Then then on a possibly augmented probability space, omega tilde f tilde p tilde xt satisfies star where star where is a feedback control. And conversely, if a feedback control is given to me, then I can make it, I can do a similar thing. So since I am not doing it as a theorem, I am stating only one part of the theorem, and this part is the most important part. That if I have an open loop control, I can make it feedback without any loss of generality. And if I have a feedback structure given to me, then I can convert that open loop into a feedback with the same structure, which I have not written. So if you want to read the details about this, the original proof is given by Borker, and he has written a book, Optimal Control of Diffusion Processes. This is a book by V.S. Borker, Optimal Control of Diffusion Processes. It's I think 88 or 89 book. The proof is given there, but the proof uses these and these as bounded. We have generalized that to unbounded, and you can see another book by Arapostathis, Borker and myself, the latest book in which we have proved this theorem in the most generality. So how do you do that? If you have an open loop control, you can make it a feedback on a possibly augmented space. Now I am not saying that, by stating this theorem, I am not saying that under a feedback control this has a unique solution. All I am saying is that if you have an open loop control, you can make it a feedback. That means on a probability space, you can create the structure where it will be a feedback. And due to this theorem, you can replace an open loop by a feedback. Now how do you prove that? The proof is simple. Proof is sketch. It's not proof. It's sketch. So I already have an open loop control. So I define a feedback control, take f belonging to CB of u. That is this f is any function which is continuous, bounded is irrelevant here. U is a compact metric space. So I define set mu bar by f of d mu bar of t is equal to conditional expectation of f d mu t given f is u is a compact metric space. I am assuming u, the control set is a compact metric space. Take any continuous function on this and define a process mu t by, since this is a determining class, integral, by an integral I define this. In other words, if you want to know what is mu t is basically this, basically the conditional expectation of mu bar of t is the conditional expectation of I mu t of A is equal to conditional expectation of mu s of A. No, this is a better way of writing it. This is becoming messy. This is a better way. So since this is a determining class, the integral of f d mu t over u is equal to the conditional expectation of f d mu t. F d mu t means, remember, this is f of u and this is a relaxed control. So this means f of little u du. So this is the definition of mu bar of t. Now by definition, mu bar of t is feedback, because I am taking conditional expectation with respect to the available information. So by definition, of course, I will take a measurable version thereof. I will construct this and take a measurable version. So by construction, by definition, mu bar of t is fxt adapted. By definition, mu bar of t is fxt adapted, and therefore it's a feedback. Now you take this mu bar of t, and then what will happen is, using martingale representation theorem, you can show that d of xt will be bt xt mu bar of t dt plus sigma of xt, some other Brownian motion. You can show using martingale representation theorem that this will be true using martingale representation theorem. So in other words, but remember one price we are paying. Suppose that my original mu is not a relaxed control but an ordinary control. It's just an ordinary control, but I am taking the conditional expectation. So even if my my original one is an ordinary control, mu bar is going to be a relaxed control. So relaxation is mandatory here. In this setup, if you want to make it a feedback control, then relaxation is mandatory. That means even if you start with an ordinary control, the equivalent control, feedback control that you will get is a relaxed one. And then if you go through a proof is, you have to go through martingale representation theorem. Using martingale representation theorem, you can prove that. And therefore, without loss of generality, you can assume that an open loop control and feedback control loop, these two setups are equivalent. And therefore, any control without loss of generality can be taken to be a relaxed feedback control. Relaxed. I again repeat the word that without relaxation, this theorem doesn't hold, because I am taking conditional expectation. Therefore, this is you will get the regular conditional distribution of this, and therefore it will be a relaxed control. Now you have a relaxed control which is feedback. So right now, without loss of generality, if I assume this theorem, then I will assume that from now onwards I will always write mu here, and I will assume that mu is feedback. This means mu t is progressively measurable with respect to the sigma field generated by xt. So it's a feedback, and under feedback I am not claiming that this has a solution. All I am saying that give me an open loop, I will give you an equivalent feedback which will agree in law. And since I am interested in only law and not the sample paths, it doesn't matter. So that's the crux of. Now you want to prove dynamic programming principle, blindly copy what Shaiju has done. It will work. The reason is we are now in the feedback situation. Once you have a feedback situation, you have to do a little bit of modification in what Shaiju has done, but by and large that will be routine. Now if you have a feedback situation, then when you are switching at a random time, switching at a stopping time, this will also be a feedback control, feedback relaxed control. So you can switch between two feedback relaxed control and get a feedback relaxed control, and therefore the dynamic, even at a stopping time, and therefore the dynamic programming principle holds. So this is the crux of dynamic programming principle. We have used two particular simplification. One is what happens if there is control here. That's an important case that the situation that I am describing will not cover. Suppose there is a control here, B of t, xt, mu t, dt, plus ideally I would like to have xt mu t here. I would like to replace, suppose there is a ut here, originally there is ut here and ut here, ut here, ideally I would like to replace ut by mu t, right? And here is the physical interpretation. Replacing un by mu n means randomization in discrete time, and in continuous time randomization is not possible because we cannot generate such things with measurable sample paths. That's a technical thing. Because if you look at normally when you construct stochastic processes, the standard theorem we use is Kolmogorov consistency theorem, right? Kolmogorov consistency or extension theorem. Remember, Kolmogorov consistency or extension theorem gives you a stochastic process with absolutely no properties. Absolutely, if you have consistent family of probability measures, then that can be uniquely extended to a probability measure. Thereby, if you can construct a stochastic process. This stochastic process has absolutely no sample path properties, not even measurability. So Kolmogorov consistency theorem, which lies at the base of the construction of stochastic process, unfortunately has tremendous limitations. You do not even get measurability. So you have to give conditions to have measurable sample paths, and if you do not have measurable sample paths, you cannot do anything. And therefore, randomization can be done in continuous time if you want, but you won't get measurable stochastic processes with measurable sample paths. Since that is a technical requirement, randomization is in continuous time cannot be done. So, coming back to the problem here, ideally this would be the physical interpretation, right? If I have to do randomization, the randomization here, the randomization here. But then if you generator of stochastic process has been done, right? Markov processes and generator semigroups, it has been done, right? Morning when I came, all A semigroups were flying around. Okay, so I presume. So it has not. If it has not been done, so suppose if you have a stochastic process like this, then the generator of that stochastic process, ut, the generator of that stochastic process for a fixed input will be an operator given by half Aij xu del 2 over del xi del xj plus bi L over del xi over I. So this will be the generator, and if you want that to study, you have to do randomization at the generator level, and if you do randomization at the generator level, this will not be the same as this, and therefore if the diffusion coefficient contains a control term, you cannot use stochastic, you cannot use relaxed control. You have to use relaxed control at the generator level. At the generator level, when you are doing randomization at the level of Aij, then you have to take the non-negative square root of aij. That will not be the same as this. If you are doing randomization here, then you will be doing double randomization here, right? Because aij is sigma sigma star. So there will be two layers of randomization, and that will not be tractable. So if you want to do randomization here, you have to do randomization at the operator level, which is not the same thing as this. So randomization is the relaxation, I am using the wrong term. Relaxation for this is done via this at the operator level, which has no physical interpretation whatsoever, and therefore normally it should be avoided. If you are dealing with a physical problem, do not do relaxation here. So we are avoiding that situation. No control here. At this level, it's fairly general. Dynamic programming principle is fairly general. Now let's look at the structure of the dynamic programming principle. So let's take instead of a deterministic time, let's take instead of a stopping time, let's take a deterministic time. So fv of tx is infimum e u tx e mu tx t to t plus delta cs xs mu s ts plus b t plus delta this is the integral form of the dynamic programming equation. From here we want to derive the partial differential equation. Now let's, you have done this, right? Deterministic, you have done this, right? So let's recall how do we do what Shaiju has done. Let's do that. Repeat again.
The smooth case I have done.
Yeah, smooth case only. I mean, I'm not going to prove it. So Vt of x in the deterministic case is infimum over control u t to t plus delta c plus v t x t plus delta. So roughly speaking, if v is smooth, then what you do is you vt, you basically take this 0 here, it's minus vt of x, and divide the whole thing over 1 over delta and take limit delta tends to 0. Assume that things are very nice, smooth, right? And then use the chain rule, right? Then what do you get? You get a differential equation del v over del t plus gradient of vtx dot product with vtxu plus ctxu infimum u. This is the so-called Hamilton-Jacobi-Bellman equation, using under the assumption that this has super in doesn't matter. It doesn't matter. So this is the Hamilton-Jacobi-Bellman equation. If the V is smooth, then you can show that V satisfies this. And of course, there is a terminal condition which is obvious. V of capital T of x is Gx. This is the terminal. So if V is smooth, then this is no problem. Then V is the value function. Now, you can test that for linear system. For example, if your system is something like this, x dot equal to some at of xt plus bt of ut. This is your linear system and your cost is quadratic. That means c of tx of u is going to be equal to some matrix q x prime q x prime qx plus x prime rx, if this is cost, and g of x is some m prime x prime mx. If this is called a linear system and this q is qt, qtx, rtx, this is also, no, this is m. Huh? Oh, RT is control, so u prime. So CT of x, this is the system is linear control system, and the cost is quadratic, x prime qt of x, u prime RT of u, gx is x prime mx. This is called the linear system with quadratic cost. If this is a linear system with quadratic cost, then you can show that this equation has a smooth solution, and the solution can be obtained via the so-called Riccati equation. You have ever seen this linear system with quadratic cost and the significance of that? Mentioned it, right? Now, if you haven't seen it, let me give you this is the basis of optimal control. This started with deviation of trajectories followed by rockets or airplanes. Now, deviation of the trajectory is very, very important, right? And you can see that if the deviation is not very large, then the deviation is always given by a linear equation, right? So, the deviation there is something called a nominal path. When a plane or a rocket takes off, you would like this to take off from a certain point and land in some point, and you want that to go through a particular trajectory, given trajectory. Every airplane, rocket or whatever, you want it to go through a particular trajectory, but it doesn't, because of various factors it always deviates from that path. If it deviates from that path, then to first order approximation, that deviation is given by this kind of an equation or stochastic differential equation. And then why is the cost quadratic? Because there is every time you are deviating from the path, you pay some price, right? For example, perhaps on the nominal path the fuel consumption is minimum. If you are deviating from that path, you pay for more. So if you deviate from the normal, you pay some quadratic cost, right? For example, the square of that deviation, the distance of that deviation perhaps you pay, and hence this quadratic term. Now, to minimize or to reduce the deviation, you have to put some control effort, right? That control is in your airplane or rocket. Every time if it deviates, you pay a price, and then you pay a further price for bringing it back to where you want, and therefore you pay the price for the state deviation, and this is the price you pay for using the control to reduce the deviation, and therefore the cost is quadratic. If the system is linear and the cost is quadratic, then this has a very nice solution, a very nice smooth solution which you can obtain explicitly, and therefore the linear system with quadratic cost is a done case. If you have a noise here, additive noise here, that means the system is governed by a stochastic differential equation also, then also similar things can be done. So, here also if V is smooth, so what is the meaning of smooth here? Smooth means V belongs to C12. Once continuously differentiable with respect to time, and twice continuously differentiable with respect to x. Suppose this is the case. Everybody is familiar with Ito's formula? Everybody is familiar with Ito's? Huh?
Oh,
No?
that lady referred.
Yes. So you know that for Ito's formula you need this, right? So let me write down the Ito's formula. For this case, let me write down the Ito's formula. So my stochastic differential equation is dxt is equal to bt xt. U will be treated as a parameter, so that will not matter. If this is my dxt, then if I have a function f which is twice continuously differentiable with respect to this, then f of txt, d of that means in the differential notation, this is going to be equal to del f over del t plus L of f x dt plus gradient some prime somewhere, right? The dimension doesn't match, does it? Something, probably this will be prime. This will be prime. So this is Ito's formula. So L is the generator. So what is L? L of ftx is equal to half trace ATX where A is this is Ito's formula, right? This is Ito's formula if f is C12. So what is the difference between Ito's formula for usual calculus and the stochastic calculus is this term, the second order term. This term doesn't come in deterministic calculus, and therefore when Shaiju derived it, he didn't have this term, and therefore when you derive the corresponding HJB equation, there is no second order term, but there will be second order term. So here, if V is smooth, then instead of using whatever Shaiju has done, do the same thing with respect to, using Ito's formula. I am just telling the heuristic. Ito's formula, the HJB equation will be a very similar equation. This will be del V over del T plus infimum U LU of VTX plus CTXU equal to 0, and V of capital Tx by definition is Gx. So this is HJB, where what is LU? LU of FTX is same as that, except that half trace a Tx d2 of d2 with respect to x of ftx plus gradient with respect to x ftx gradient with respect to ftx dot btxu. So this is LU. So for each fixed input, this is the generator of the control diffuser. This is a second order operator. So if V is smooth, then you can prove that this is the HJB equation. That can, the proof will be heuristic, but the proof will go through. If V is smooth, then this is the case. There is absolutely no problem. Now, the question is, you have any question on this? Because this is the basis of stochastic optimal control, the derivation of the HJB equation. Or I can do the heuristics. Would you like me to repeat the heuristics? So basically is, if you want Vt of xt, you write. Okay, the heuristic goes like this. Let me write down the heuristic. It's not, I am not deriving HJB. Nobody derives HJB. One guesses. Remember, most of the time we do not derive HJB. We make a guess of what HJB is, and then we look at the HJB. Derivation can be sometimes because the derivation will demand that it's smooth. If you want to really derive the HJB equation, the derivation will demand that it's smooth, and a priori we do not know if it is smooth. And therefore, one does not derive. This is the dynamic programming. Right? So dynamic programming is basically, you bring this to that side, and then you divide by delta, and then let delta go to 0. Then you will get the derivative of this. Right? Now the derivative of this in the deterministic case only involves derivative with respect to time and space. Right? And the derivative, but whenever you involve derivative with respect to space for V, there will be a second order term. And that is why this comes. Or to put it otherwise, you look at this equation. Assume that this is smooth. And for the time being, never mind the infimum. Never mind the infimum. Take a fixed input u. Take a fixed input u and do the derivation. So take a fixed input and do the derivation and write down what is V of txt. Would be, if the input is fixed, not a control but an input is fixed, V of txt is going to be equal to, write down the Ito's formula. So write down d of this. D of this. So this is going to be equal to del V over del t, t of xt plus Lu of V of t xt, this dt plus then we will get this V of txt sigma of txt This is what you will get. Now integrate between t and capital T. This quantity, integrate between t and capital T. Right? If I do that, then I will get v of t x of t minus v of t x of t. Right? I will get this, right? And this will be equal to, let's not do this capital T, but let's do this. This is informal. Huh? This is very, very informal. T plus h. This is not a proof. This is the idea behind the proof. Then you have this bracketed quantity, del V over del T plus LU V S excess ES plus T to T plus H, this quantity. Now take the expectation. Now if you take the expectation, this term drops. Right? And then you will get this. Very informal. And then you have done this for a fixed U, and then you pretend that infimum fits in. So remember that we did not derive HJB equation. HJB equation, because this derivation that I have written assumes that V is smooth, and I have absolutely no information about the smoothness of V, and therefore HJB equation is not derived. HJB equation, what we say is that we use a particular jargon in stochastic control using DPP heuristics. Using DPP heuristic, this must be the solution. So it's a heuristic argument that we derive this solution. Okay, the heuristic is based on Ito's formula. Now the question is, suppose this equation has a smooth solution, then what can you do? Right? Suppose, so this is my HJB. Now here is something called verification theorem. This is called verification theorem. Verification theorem. So this is the HJB equation. Again I repeat, HJB equation has not been derived, HJB equation has been guessed. So if you compare it with the first order, the only difference is that you have a second order term coming, and the second order term is coming because the chain rule of deterministic and stochastic calculus are different. In stochastic calculus, you have a second order term. Now what is the verification theorem? If the HJB equation, again I will put it as quote because I will not, if the HJB equation has a smooth solution phi tx, then phi tx is equal to Vtx. If HJB equation has a smooth solution, then suppose the smooth solution is denoted by phi tx, then that phi tx is going to be equal to Vtx. What are the consequences of this? That if the HJB equation has a smooth solution, then the smooth solution is unique and is the value function, which in turn tells me that the value function is smooth, and therefore the dynamic programming heuristic is in fact rigorous. So everything boils down to a PDE. Here is a PDE, right? Now this PDE, if you look at the PDE, how do you prove this? Again, since the theorem itself is undercode, the proof will be severely undercode. Okay, so what is the proof? So take this minimizer. For every u, I have said that this u now belongs to a compact metric space, right? So for every u, this infimum is a minimum. Remember, there is a big difference between infimum here and infimum here. What is infimum here? The infimum here is over all stochastic processes from Tt taking values in Pu. Oh, so I have infimum over, I have infimum with respect to mu, infimum mu belonging to Pu. Sorry, I got carried away by u. These are all mu, relaxed control. So everywhere I have mu, that means everywhere I have integration. This is mu. I have integration everywhere. So that doesn't change, because u, if u is a compact metric space, then so is Pu. Pu is also a compact metric space. That doesn't change anything. So everywhere, if there is a, for every u I determine, if I put mu here, that means I am integrating with respect to mu. Now, how would you prove that V is smooth now? So take any control here and apply Ito's formula. Ito's formula will give you an inequality. Take any control. Take any control, mu t. Take any control mu t and apply Ito's formula. If you take any control mu t, what will happen? If you take mu t, then infimum is equal to 0. So if you put any other control, what will happen? There is going to be an inequality, right? Which way inequality? This is what I get always confused. Del V over del T plus L mu V of Tx plus Ctx mu T will be greater than or equal to 0 or greater than or equal to 0, right? This is going to be equal to greater than or equal to 0, right? This is going to be greater than or equal to 0. Now apply Ito. Apply Ito. Then you will get Vt of x will be less than or equal to E of mu Tx just Ito's formula. An application of Ito's formula will give you less than or equal to. If you take any control mu, then you have an inequality of this form. Apply Ito's formula, because V is smooth and V satisfies this inequality, you will automatically get that Vt of x is less than or equal to this quantity. Now take the minimum here. The infimum will be attained. Under suitable conditions, infimum is going to be attained. If infimum is attained at a point, then that's going to be a function of mu is going to be a function of t and x, and that function is going to be a measurable function, right? Under that measurable function, if the stochastic differential equation has a solution, right? Suppose the infimum is attained at mu star, then you can prove that Vt of x is equal to E of mu star of Tx, the same thing, where mu star is the one that attains the minimum here, and the minimum will be a function of t and x. Now that will be a measurable function of t and x, and you have to use a suitable measurable selection theorem to do that. Use a measurable selection theorem. If this is a compact metric space and continuity are there, you can always find a mu star, a function of Tx, that follows from by axiom of choice, but then you have to apply a suitable measurable selection theorem to ensure that this mu star, where the point-wise minimum is attained, is also a measurable function, because without measurable function we can't do any analysis, and then again apply Ito and you will get an equality here. So it's less than or equal to for any mu, and for a particular mu star it is equal to, and therefore V must be equal to this. This is the infimum. Now there is a big difference between this infimum. Remember, this is infimum with respect to all stochastic processes mu, and here the infimum is only over a particular probability measure mu. So this is a static optimization problem. For each Tx, you are solving. So this is the so-called Hamiltonian. This is called the Hamiltonian. It has come from physics. Instead of an abstract problem, if you had taken the classical, the problem brachistochrone, for example, then this will be the so-called Lagrangian. Okay, and this is now a static problem. That means for each Tx, you are just minimizing this quantity. So minimizing the so-called Hamiltonian, and the minimizing Hamiltonian, it's called the minimizing selector, is becoming an optimal control. So this optimal control is given by the minimizer of this. Now the minimizer is going to be a measurable function of t and x. The question arises, does there any solution under a measurable Tx? That I will address tomorrow. Now the thing that I want to say in 1 minute is that here is a mu, right? Here is a mu, and look at this. This function, this is a linear function in mu. With respect to this mu, this is what is this mu? What is Ctx of mu? Ctx of mu is u Tx u mu du, right? This is Ctx of mu. So with respect to mu, it's linear, right? And where are we taking the minimizing? Minimizing is Pu, right? Pu is compact and convex, right? And here also the same thing, linear, and the minimizing is over compact and convex, and therefore the minimum will be attained at an extreme point. If the minimum is attained at an interior point of Pu, it will also attain at a extreme point, and the extreme points of Pu are the Dirac measures, and therefore here I can replace this mu by u. I do not need. I mean, there are many ifs here. Basically, I haven't proved anything, but I have started a process. That if all these things are true, then I don't need relaxed control. Because if there is a relaxed optimal control, there will be a usual optimal control. The reason is, if there is an infimum at an interior point, by compactness and convexity, there will be an interior at an extreme point, and the extreme point are the Dirac. So the question is, when does this have a smooth solution? That I will discuss. My time is up, right?
Discuss tomorrow. Just what is the maximum smoothness you get?
Huh?
What is the maximum smoothness?
Maximum smoothness if in the uniformly parabolic case, right?
Yeah.
See 1 plus gamma.
No. 2 plus
2 plus gamma and 1 plus gamma by 2 or something.
1 plus
Something
gamma or 1 plus delta, right?
with the same with the gamma.
Same
by,
gamma, can you do this?
No, gamma by 2.
Gamma by 2, right? This is the smoothness that you can.
Provided your C is Holder continuous.
Yeah, no. That I started with all ellipses, right? No. If it is Holder, then you can't do this. This is for ellipses. This is for ellipses. If it is Holder, then the Holder exponent will come here. If it is Holder, if it is gamma Holder, then Holder will come here.
This is for
And
d
Holder
gamma.
will come here. And if it is this ellipsis, then provided it's uniformly parabolic.
Sorry, this is the extreme smoothness that you can do.
The maximum smoothness.
This is
In
by
general.
interpolation.
Huh?
This is done by interpolation.
This is done by?
What method to
Oh, this is done by what is called parabolic regularity. That by parabolic, I will talk about that. Parabolic regularity.
it's the interior shoulder estimate?
Yes. We will. That those things will come. I am not going to do that, but that's the basics.
But
This is how
That's the method.
the product should be.
Parabolic regularity. In fact, I have learned
One is there.
asking me the question. Okay, so tomorrow.